Welcome to the presentation of our paper, Harmonizing ARINC 653 and Real-Time POSIX for Conformance to the FACE Technical Standard. I'm Gadir Bloom and did this work jointly with Joel Sherrill. We are both maintainers of the open source real-time operating system RTEMS, and this paper is an industrial experience paper related to use of RTEMS in a commercial product. The FACE Consortium was started by U.S. Navy NavAir and U.S. Army Aviation to provide a well-defined and common operating environment that enables portability of software components across multiple systems. The FACE Consortium operates under the Open Group and now has approximately 100 member organizations from industry, government, and academia. The consortium's primary product is the FACE Technical Standard, which is now at edition 3.0. The FACE Consortium operates a formal conformance program which defines the process by which a unit of conformance, or UOC, is independently verified to meet the requirements of the FACE Technical Standard. A conformance test suite automatically verifies many of the requirements, while others use evidence provided by the software vendor. The FACE Technical Standard defines the FACE reference architecture. The FACE architecture was introduced in edition 1.0 with 5 core segments that remain to this day: the Operating System segment, Portable Components segment, Platform-Specific Services segment, I/O Services segment, and Transport Services segment. The basic functionality of each segment is the same over time, although the interfaces have undergone significant changes, migrating from procedural-style interfaces toward an object-oriented approach and adoption of interface definition language. The Operating System segment incorporates existing operating system, programming language, and graphics standards based on their use in safety-critical avionics systems. The FACE Technical Standard defines 4 profiles which reflect usage patterns and products at different levels of criticality. The Security, Safety Base, and Safety Extended profiles require the ARINC 653 avionics software standard, along with an increasingly larger set of POSIX methods. In the General Purpose profile, ARINC 653 is optional, but a larger set of POSIX methods is required. The POSIX standards body defined 4 real-time profiles of the 2003 edition of the POSIX standard, identified as PSE 51 through 54. The FACE profiles roughly align with those 4 profiles, but are based on POSIX 2008. The FACE profiles take into consideration safety and security concerns such as reentrancy, as well as addressing methods which have been deprecated or obsoleted over time. Here, the last column shows what % of methods included in a FACE profile are shared with a closely corresponding POSIX real-time profile. Recently, there have been efforts to align the FACE profiles with those of the software communications architecture application environment profiles that are used by software-defined radios. The FACE profiles reflect common industry practices. Operating systems, which address higher levels of criticalities, tend to support only the methods in the more stringent profiles. Similarly, applications are designed to only use those methods. This reflects both the capabilities of the systems themselves and concerns over qualification efforts. By 2015, the FACE Consortium had begun to establish its conformance program. Joel Sherrill had been tracking the open source RTEMS POSIX capabilities against the FACE profile since edition 1.0. It was clear that RTEMS would never be a FACE-conformant RTOS without ARINC 653 support. Similarly, DDCI had realized that Dios met the ARINC 653 requirements but did not support POSIX. In stereotypical fashion, at a hotel bar during a FACE meeting, Joel and a DDCI person sketched out the solution on a napkin: paravirtualize RTEMS and run it in a Dios partition to provide POSIX services. Their idea turned out to be correct, but ignored a number of details required to produce a working, nicely integrated product based on Dios and RTEMS. The napkin moment was the realization that there was a technical solution to solving a business problem. Avionics qualified RTOSs are very expensive, with Wind River and Green Hills historically dominating the market. The Dios plus RTEMS solution offered a lower technical effort path to achieving FACE conformance. The paravirtualization of RTEMS to run as a guest on Dios required much less effort than DDCI developing the required POSIX APIs or OAR developing the required ARINC 653 support for RTEMS. In addition, this allowed other RTEMS capabilities to be available on Dios, such as the file systems and state-of-the-art TCP/IP and USB stacks. Together, Dios plus RTEMs provide a much richer runtime environment than either alone and beyond what is strictly required by the FACE technical standard. Dios is a commercial ARINC 653 RTOS that provides time and space partitioning with a consistent interface across architectures, allowing reuse and redeployment of qualified subsystems without recompilation on the same architecture. Dios originated at Honeywell and has a long history of use in commercial avionics. RTEMS is an open-source RTOS with hard real-time and POSIX support. It was originally developed by OAR Corporation for the U.S. Army, but has always been open source. All services for the RTEMS project are currently hosted at rtems.org. Source code repository, documentation, tickets, tracking, wiki, mailing lists, BuildBot, etc. RTEMS has a heritage of deployments in safety-critical systems across a variety of domains. The European Space Agency has publicly acknowledged performing safety qualifications on earlier versions of RTEMS for internal use and is currently supporting an effort underway that is working with the open RTEMS community to provide technical data required for qualification efforts to be available from the open source project. As an ARINC 653 RTOS, Dios provides time and space separation. Each partition is a separate address space, which allows applications to execute in unprivileged user space. This protects the kernel from applications and applications from each other. RTEMS was paravirtualized to enable it to execute in the unprivileged partitions. RTEMS already had some support for paravirtualized environments, which addressed basic issues like avoiding supervisor mode instructions. And this integration effort added to the paravirtualization tailoring points. For example, RTEMS, when executing on Dios, can make memory configured to be shared between partitions available to an application via the POSIX shared memory and memory mapping APIs. The same POSIX APIs are available in non-paravirtualized RTEMS, but there is no host environment to provide separation of address spaces. By taking a paravirtualized approach, the bulk of RTEMS is unmodified, and only an adapter layer had to be provided. This slide outlines some of the key challenges we discovered while integrating RTEMS as a paravirtualized guest under Dios. Each of these areas will be discussed in detail in the upcoming slides, and many more supporting details are available in the paper. First of all, Dios is not a hypervisor, so it does not have a hypercall interface. And so we had to implement an adapter layer to provide the equivalent of a board support package to tailor RTEMS toward Dios as the underlying hardware, if you will. RTEMS already had a configuration point to enable paravirtualization. This had to be augmented to allow for access to more capabilities in the host Dios environment. Additionally, there are some specific Dios and RTEMS adapter APIs which allow for access to information like boot arguments and environment variable settings, which are provided by the system integrator as part of configuring a partition. One of the first challenges we identified was that the POSIX and ARINC 653 execution models are quite different. POSIX defines a very dynamic environment consisting of processes and threads which may have priority. ARINC 653 has partitions that are comparable to POSIX processes in terms of address space containers, but partitions are manually scheduled by the system integrator in a static, predefined partition schedule. Input or output from a partition is strictly controlled based on the static configuration. Within partitions, ARINC 653 has what it calls processes, equivalent to threads or tasks, but the set of services available is quite small. These are also static. The hard question to answer was, how much time passed while my RTEMS partition was not executing? To address this, an exception is handled at the start of each partition window by the RTEMS adapter to determine how much time has passed while it was not executing, and it advances time inside its partition to account for this. After this occurs, all threads begin to compete for the processor based on priority. Additionally, there are no clock ticks that occur while a partition is executing. RTEMS can obtain an accurate timestamp by obtaining the current uptime from Dios and using that to determine how much time has passed since the partition began to execute. Adding these two time values results in a monotonically increasing nanosecond accurate timestamp and time of day source. One of the FACE operating system segment requirements is that when the time of day is set, it must be set across all partitions. This was not supported by RTEMS because normally it executes by itself on a processor and has no concept of other partitions. A hook was added, which allows a board support package or application to perform a system-specific action when the time of day is set. This has been merged to the rtems.org source upstream. When an rtems partition begins to execute, the adapter will determine if the time of day has changed, and if so, change the current time of day in the local partition through the registered hook. Dios was enhanced to have the ability for the system time bias to only be settable by one partition as required by FACE. RTEMS is a single address space operating system which provides multiple threads within the logical context of one POSIX process. It assumes that it has full access to the entire address space. Assuming that the executable is loaded into RAM, all memory past the executable image is allocated to RTEMS for use by the C program heap, RTEMS workspace, and thread stacks. Dios uses a special memory area for thread stacks, which is marked as for thread stacks only, that generated an exception when RTEMS did not use that area. RTEMS supports having a BSP or application-specific thread stack pool with allocator and deallocator methods. This was used to allocate RTEMS thread stacks from the memory reserved and protected by Dios. On some hardware platforms, RTEMS makes limited use of a memory management unit to do things like protect code space from being overwritten. But as a hard real-time single address space operating system, there's never been a requirement for virtual memory. So the POSIX shared memory and memory map interfaces are of limited use and were not supported by RTEMS. These were implemented under this effort without adding virtual memory to RTEMS as a functionally limited implementation using memory aliasing and copying. When RTEMS is executing on Dios, Dios can have memory configured to be shared between partitions. This memory is then made available to an application by the POSIX shared memory and memory mapping APIs. The same POSIX APIs are available in non-paravirtualized RTEMS, but there is no host environment to provide separation of address spaces. Despite that limitation, others have found the support useful for application portability. The FACE technical standard requires that a subset of the ARINC 653 APIs be supported for use from POSIX applications. The ARINC 653 sampling and queuing port APIs are provided for inter-partition communication by the Transport Services segment. The ARINC 653 health services must be provided to allow for partition error handling and restart. DDCI refactored their ARINC 653 implementation in Dios to provide a plug-in point for OS-specific scheduling and thread management support. Further, they provided the FACE-required subset of ARINC 653 APIs in a FACE 653 library, which is used by POSIX partitions. The RTEMS Dios adapter has software which plugs into this FACE 653 library and adapts it to use RTEMS blocking and scheduling primitives. This allows the core of the ARINC 653 implementation to be used unchanged by POSIX or ARINC 653 applications. This was a successful effort in that the Dios plus RTEMS product has achieved conformance to edition 3.0 of the FACE technical standard on the PowerPC. A new baseline is being taken through FACE verification as a delta on the safety-based certificate, and other processor architectures will be variants on that updated FACE verification. Ultimately, all POSIX additions and paravirtualization enhancements to RTEMS have been submitted to the open source project and are available today. Although source lines of code, or SLOC, is generally considered a terrible measure of productivity, in this case, some useful insights can be made from the SLOC. The highlights of this table are that 3,037 lines of code are architecture independent and shared across all architectures, and less than 250 lines of architecture dependent code is present in the adapters. Almost half of the code written was for Dios plus Artem's specific tests. The effort needed to add a new architecture is quite small, with only 5 lines of code added to provide ARM support. Importantly, from our perspective as open source maintainers, approximately 19% of the code was submitted upstream back to the artems.org public Git repository. Credit also should be given to the DDCI engineers we worked with, who helped identify clean, clever, and small solutions to the integration challenges on their side. In conclusion, this was a successful effort. This is a shipping product for the ARM, PowerPC, and x86 architectures. Neither Dios nor Artems had significant modifications as part of the integration effort. This is aligned with 2.1, 3.0, and the upcoming 3.1 editions of the FACE technical standard. The open source Artems provides a solid foundation of paravirtualization configuration points, which should enable future similar efforts.